Just like with the aldol condensation, the Claisen condensation can also be carried out intramolecularly, specifically to close a 5 or 6 membered ring. When the Claisen condensation is carried out intramolecularly, we have a different name for it, and we call it the Dieckmann condensation. Dieckmann was the first chemist to demonstrate the possibility to do the reaction this way. It is also sometimes called a Claisen cyclization because you are actually doing a cyclization, taking a molecule with a functional group on each end and bringing the two ends together to form a ring. Okay, so depicted on the screen is an example of this reaction. In this case, we have a 1,6 diester. Okay, so 2 esters, and then there are 4 carbons in between the 2 esters. So if you take this starting material and treat it with sodium ethoxide as a base, remember we need to use the base, ethoxide as a base if we have ethyl esters, methoxide as a base if we have methyl esters, etc. So treated with sodium ethoxide as a base, followed by the necessary protonation in order to generate a neutral product, this now gives us a cyclopentanone with an ester sticking off the carbon alpha to the ketone. In other words, this is a beta keto ester. So an appropriate starting material for such a reaction, if you want to close a 5-membered ring, is, as we have seen here, a 1,6 diester. If you want to close a 6-membered ring, the appropriate starting material is actually a 1,7 diester because you're going to need 5 carbons in between the 2 esters. Okay, so let's look at the mechanism for this reaction. So the first step is using ethoxide as a base to remove the alpha hydrogen and generate the enolate. Okay, so in this case, we're keeping the molecule drawn consistently. We are removing the alpha hydrogen from carbon 2. Then in the second step, that enolate attacks the carbonyl group at the other end of the chain, which in this case would be carbon 6. That's going to generate the tetrahedral intermediate. And then, as is common for all reactions in which a nucleophile adds to an ester, you're going to regenerate the carbonyl, and then you're going to expel the leaving group, which in this case is ethoxide anide. And then, as is always the case for a Claisen condensation, there is an alpha hydrogen that is now alpha to both the ketone and the ester. So this will be an incredibly acidic hydrogen. It's going to get removed completely and irreversibly by ethoxide. And you have to remember that this 4th step is what actually drives the 3 steps that came before that, because as the arrows are shown in the mechanism, all 3 of those steps are actually unfavorable equilibrium. But then the 4th step, the deprotonation, drives all of them forward to products, and then it's just going to sit there as the very stable double enolate until you add aqueous acid in the workup. That's now going to protonate that central carbon and give you a neutral product. Okay, so mechanism is the same as a normal Claisen condensation, except we're carrying out the reaction intramolecularly, and it is therefore called the Dieckmann condensation.